Hello and welcome. Today we're going to be talking about solving the wave equation with fixed endpoints. So let's draw a picture of what we're talking about. So first there's the wave equation, and that's simply the second time derivative of u is equal to c squared, the second time derivative in space. Okay, and so this is for x in the range from 0 to L. Okay. All right, so that's one piece of the puzzle. And then, of course, the ingredients to a problem, which actually will elicit a solution, we need also boundary conditions. In this case, we're going to be talking about fixed endpoints. So we're going to set u of x equals 0, comma t is equal to u at x equals L, comma t is equal to 0. Okay, and then so that's one thing, and so now finally we need to talk about initial conditions. Okay, so there's actually two initial conditions here. Because we're talking about a mechanical system involving masses, so another little point we need to write down here is that c squared, this quantity, is equal to the tension on the string divided by the mass density. Okay, and so because we're talking about a system with mass, with inertial aspects to it, we need to have an initial position and an initial velocity. And again, what we're talking about here is a string that's at x equals 0. We have u is equal to 0. So u, the u-axis is, of course, the vertical displacement at every point on time on this, at every point in space and time on this string, and that's also u is equal to 0, that neutral point there. So in general, the string can vibrate up and down at all places. And so we need to find out if we can find a solution to this. So we're going to call this u of x, t equals 0, is equal to f of x, and u of x. So this will be the time derivative now. U of at t equals 0 is equal to g of x. So because this is a system with mass, with a mass density, and there's forces involved, we're talking about a system, a second order time system, because of this is, of course, an acceleration term. Because that acceleration term is there, we're talking about a system that has both, can be bent and sort of distorted out of position. That's this function here. We're stretching the spring and stretching the string and displacing it like we would pluck a guitar string. But we could also impart a little velocity into the string itself. The string could have some velocity as well as a distorted position when we start out, and that can lead to motion of the string. So both pieces of data are important, just like if we have an acceleration. If we have a second order ODE involving an acceleration, we need both an initial position and initial velocity initial conditions. All right, so that we'll call f of x and g of x, right? So you can think of this as, like, if this is f of x, this profile here, g of x tells you how each point of mass has a certain velocity and direction. So we might actually you might want to draw, sort of indicate the velocity. We'll erase those as being sort of like an arrow that emanates off this position. So here we're talking about that although this string is bent here, the string as a whole, as we go to the next moment in time, everything is going to be moving up a little bit. That string wants to keep going up. And here we can think of it as, at this point, every point in the string wants to go down. And so This is sort of like, not only if we stretch the string at the beginning, we've also are pushing it, actively pushing it at the beginning of time, at the beginning of when we start modeling our system at time equals 0. Okay, so with all of these ingredients, we can find a solution. So the method, our time-honored method now is, of course, the separation of variables. Something we know a lot about, and I'm sure we're getting more and more familiar with the logic. So let's go over this. So just like before, we have a, we're going to guess that u of x comma t is actually going to be equal to p of x times q of t, just like we're used to. And now we're going to put it into the PDE. So we have UTT is equal to c squared UXX, and that becomes Q double prime times P is equal to c squared Q times P double prime. And what we can do then is we do the separation step, where we separate variables, and now we have a Q double prime over Q, and I'm going to put that c squared down there, and then I'm going to set that equal to P double prime over P, and then as we always do, this is a function of t, that's a function of t, this is a function of x, that's a function of x. And when you have a function of t on one side and a function of x on the other side, and they're both equal to each other, then they have to be equal to some constant, which we're going to call negative lambda, and that is unknown. So now we need to determine lambda by solving the p equation, subject to boundary conditions. All right, so we have the standard p double prime is equal to negative lambda p, and that elicits solutions of the form p of x is equal to a cosine square root of lambda x plus b sine square root of lambda x. Okay, good enough here. Now we know that the boundary condition, we take in the boundary condition, which we know that at x equals L for all time is equal to x equals 0 at all time. Those are both equal to 0, which would imply that A, in this case, is 0, and that B is free. So B is yet undetermined, and now we need, and it also, B is free, and square root of lambda has to be n pi over L. Okay, well, that would also imply then that lambda is equal to n pi over L quantity squared. All right, so now lambda is no longer unknown, and we have a set of functions Pn of x are equal to sine n pi over L x. That's a set of functions. So now we go on, of course, to solve the Q equation, which is very similar. It's Q double prime is equal to negative c squared lambda Q. All right, so we know what lambda is. We actually have a whole family of these equations to solve, one for each n. So we have Q double prime n is equal to negative c squared n pi over L quantity squared is equal to Qn. Notice that this whole thing here is positive, because we're talking about two squared constants, and we have a negative sign out there. So the solutions then have to be of the form q of t is equal to a times cosine c n pi over L times t plus b sine times c n pi over L times t. All right, so as yet, and so that's Qn. That's a whole nother set of functions there for our solutions to the time equation. So now let's write these down. So we can write down our full solution now. So u, of course, un is going to be x comma t is equal to, we'll write it as p of n of x times q of n of t, and we can write that as sine n pi over L x times the quantity an cosine c n pi over L t plus bn sine times c n pi over L t. All right, so now you have to wonder then, how do we find an and bn? Are there ways we can constrain these values? Well, the question then is, we use initial conditions. And of course we have two of them. The first one is that, and so we know from before that that there's the principle of superposition. Superposition, that if un plus um are both solutions, un and um are two solutions, then un plus is a superimposed solution. And so we can always write down a whole solution can always be a linear combination of all of these solutions, in which case we have the sum from n is equal to now 1 to infinity, because we're dealing with a spatial sign term. So n equals 0, it doesn't matter at all. And that's going to be sine n pi over L x, quantity an cosine c n pi over L t plus bn sine times c n pi over L times t, all with a parenthesis there. So that, of course, is our series solution. All right, so now we're going to use our initial conditions to find an and bn. So first of all, we'll talk about the initial position. So t is equal to 0. So we put a t in for 0 here and here. And the sine term, of course, goes away. And we're left with n equals 1 to infinity an. And the cosine term, if I put a t in there, becomes 1. Becomes sine n pi over Lx. So we have a sine series. Okay, so that looks pretty good. So, of course, the sine series is very easily solved. We can use our orthogonal projections. To get a Fourier series, the coefficients. which is an is equal to 2 over L, integral from 0 to L of f of x times sine n pi x over L dx. All right, so now let's talk about how to get the initial condition for velocity. Okay, so that should help us find, because we still need to find the bn's, right? We need to find those. So we're going to find those by doing the initial velocity. So the goal now, the final goal is to find bn's with initial velocity. Okay, so we know that the partial of u with respect to t for x and t equals 0 is equal to g of x. All right, and we know that u of x comma t now is going to be this sum from n equals 1 to infinity of sine n pi over Lx times the quantity an's, which we know now they're the orthogonal projections onto f of x, our initial position. But now we need to find these bn's. Okay, so what we need to do is, of course, take the derivative of u and then set it equal to, and set the time equal to 0 and make that equal to g of x. But we know we have an issue, right? Which is term by term differentiation. Can we do it? Well, what do we need to assume? We need to make sure that u of x, that u of x of t, when periodically extended, is continuous. We assume, I'll put that in an asterisk, assume that f and g are piecewise smooth. But do we have continuity of u? Certainly yes. We have continuity in x. Because we're talking about a periodically extended function, which is a sine series, so whatever we have here, here's our sine, and we periodically extend it. Here's L, and there's 0, and then it goes to negative L, and then it would come back around here. So for every term, we always have it passing through 0 because of the fixed ends. Every single one of these sine terms, for every n value, all pass through 0 at those points. And so, and we know that our initial condition has to do the same. That would violate a constraint of the problem. So f has to be continuous. It has to be because we're talking about an unbroken string, and it's certainly true that our Fourier series also reflects that same constraint on our modeling, is that we're talking about a connected string. And so it's certainly true that we can do term by term differentiation. So we'll take that derivative and we'll pass it through the summation, the infinite summation, and it's going to go right by the spatial sine function, and it's going to now go c times n pi. I'm going to back this up here. It's going to go c times n times pi over L times an, and that'll be a sine cn pi over L t, and then a plus bn cosine. So this will be a negative. There'll be a negative sign there because we're taking the derivative of cosine, and that'll be c n pi over L times t. All right, so that looks good. So now, of course, we're going to put t equals 0 in there and there. And of course, this whole term is going to go away because there's a sign there, and sine of 0 is 0. And so we're going to get another sine series. So g of x has to equal to the partial of u of t evaluated at t equals 0, and that's going to be equal to the sine series n equals 1 times to infinity of c n pi over L times bn times sine n pi x all over L. Okay, so here we go. So now we know that then the orthogonal projection bn is just going to be equal to, just as we've seen before, 2 over L. But now we have to just multiply by L over n pi over c. So we have to have an L over n pi times c. So the L's cancel. Integral 0 to L of g of x times sine n pi over L x dx. Sorry for cramping my writing there, but I understand that you can probably sort that out. So we have now the Fourier coefficients for the initial velocity term, the initial velocity condition. All right, so putting all that together now, we have a nice way to solve this equation. So now I'd like to get in this last little bit is just some interpretation. All right, so let's consider only an initial displacement. So we're saying then that we're saying that g of x is equal to 0, and we'll say f of x is just some function. So what do I mean? So let's just so now that means then the solution is going to be u of x comma t. So when g of x equals 0, that also implies, of course, that the bn's are all 0. So that makes our solution a lot simpler. It's just going to be n equals 1 to infinity of bn times sine n pi over L times x times now okay, and this will be times cosine c n pi over L times t. Okay, so that's our solution now, our simplified case. So from here, of course, and then of course that these are from the orthogonal projection, just like before as we had written. So those, of course, will help us approximate that initial condition. All right, that initial position function. All right, so with this put in place, so now we need to. I want to just bring into something a standard trig identity. So we know the following is true, that sine of A times cosine of B is equal to always sine A plus B plus sine A minus B. And that's all to the times 1/2. Okay, So this trig identity is going to help us. We see we have a sine term and a cosine term. So now we're just going to rewrite this series a bit. We'll bring this down here. Continue our work. And we're going to have sum n equals 1 to infinity. And that's going to be equal to bn. And now I'm going to put a over 2 there from this 2 that's sitting there. And we're going to get a sine n pi over L, and then we're going to add the a and the b together. In this case, a is equal to n pi over L x, and then b is equal to c n pi over L t. All right, and that's going to be x minus, there'll be plus c t, like that, and then we have a plus, and then we go to the other term here. We have a sine of n pi over L x minus c t. All right, and then we finally put parentheses around all of that. Oh, I put square parentheses here just to contrast. Okay, so I'm going to break this up into two pieces. And we're going to have now a sum, n equals 1 to infinity, of bn over 2 times sine n pi over L x plus ct plus another sum now, n equals 1 to infinity of bn over 2 sine n pi over L quantity x minus ct. All right, so there we go. Now we have this function here. We can think of this as sort of a, I'm going to call it, we'll call it WL. I'm going to call this one I shouldn't say of t, I should say x comma t. Actually, I'm going to go a little further. I'm just going to call this w of x plus ct, right? And here I'm going to say that this is going to be plus w x minus ct. And notice that this w function, w, now I'm going to call w, I'm going to use a fancy parameter that I'll just call it c, and that's going to be equal to this Fourier series, whatever it is, bn over 2, it's a sine series of n pi over L times c. And of course, this is of course exactly 1/2 f of c, our standard initial condition. So what we see here is that this w function is half the size of our initial condition, but we see because there's this minus ct that this is a right-going wave. A right-going wave. And this is a left-going wave because there's a plus sign there, left-going. All right, so let's just get another sheet of paper out here. I'm going to rewrite this. I'm going to do some visualization here now. So we have w of c is equal to f of c, all right? F of c divided by 2. And so our function u of x comma t now can be written as f of it'll be written as w of x plus ct plus w x minus ct. All right, so what does this look like? So if I just draw a real line here, put 0 right there, there's an L, there's a 2L, a 3L, and a minus L, a minus 2L, and so on, right? So now if I have some initial condition, let's say my initial condition, which I initially or originally just thought of as being on 0 to L, and I haven't thought about anything out here, right? There's nothing out beyond it. I can just put some drawing here, a little hump. Maybe that's my W. So I can put that there. All right, and we see now, we can think of remember the Fourier series are actually periodic extensions. So there's going to be another one right here, identical. Everywhere you look, there's going to be one. All right, so this is for time equals 0, right? So when time equals 0, you'll put a 0 in there and a 0 in there, and you're just going to get w plus w of x, and that's going to be, and both of those are half f, so 2 halves make a whole, and you get exactly the initial condition that you wanted. Now, because these are periodic extensions, they're repeated for other domains outside of the specific one we're interested in. What's going to happen, of course, is that w, now anytime you have an x minus ct, that's going to cause a wave motion going to the right. So I'm going to draw now time going forward a little bit, maybe equal to delta t, some small time forward. So we're going to have the same thing, but what we're going to have is then there's some sort of motion of a wave going here and some sort of wave going there. But then there's going to be, I should say this is an odd periodic extension. You know, I drew this all wrong. Sorry guys, I made a mistake. This has to be the odd periodic extension. So that'll be like that. Okay. Made a mistake. Looks like that. Okay. And that's going to cause this to move this way. And we're going to see basically there's a rightward motion and there's also a leftward motion of this thing. This wave is going to go that way. It's going to split into two pieces, each halves. And then the other wave is going to move that way. And the idea here is that we're going to see this wave essentially split into two pieces, two halves. And so here's the initial bit right there. One half of it's going to go that way, and the other half is going to go that way. But when it crosses over the 0 point, it's going to go negative on the negative side. And so, so this is a really interesting thing. And so, as it keeps going down, what you're going to see is basically these two wave solutions essentially always passing through each other. One going in the leftward direction, and one going in the rightward direction. So that gives you an idea of the nature of these wave solutions. And we'll study this a little bit more in detail. And in the next video, I will present some actual animations of this sort of thing for specific wave solutions, if my artwork isn't good enough for you. Thank you very much.